Okay, students. So now we will do this activity in order to understand the characteristics of hydrostatic pressure. So when we say hydrostatic pressure, the pressure exerted by liquids. So to understand the first characteristic, that is how pressure is exerted by the liquids, we are going to do this activity. So to do that, I have this polythene bag. In this, I have randomly made holes in all directions and at all levels. And also, I have a container to fill the colored water, and in this bucket, I have colored water. You all know the reason why we need to use colored water. You can just use normal water, but it's not clearly visible. So, if we use colored water, you can see how it comes out through the or exits through the holes of the polythene bag. So now I am going to do the activity. You all need to observe closely how the colored water exits through the different holes. So we need to fill the bag. A polythene bag is ideal, but we should make sure we don't crush the bag. We just need to hold it up. So now that I have filled it, I will just lift it up. Now can you all see how water exits? From all different sides, I will turn the bag slowly. You can see. Can you all see, students? From all the holes, the water exits out, and look at the way it's coming out. You all can see a difference in the way it exiting, but through all the holes it exists. From all directions as well. All levels as well as all directions. And also you all can observe, students, when the amount of water decreases, the speed with which the water exits through the holes decreases. That is because the amount of water is less, but still you can see through all the holes water is exiting. So from that observation, what can we conclude? What can you all understand? Now I had holes throughout the bag at different levels and also in all different directions. So then from this we can conclude and say that pressure is exerted in all directions by the liquid. Here it is water, but by all liquids, pressure is exerted in all different directions. Okay, students. So now we will try to demonstrate another characteristic of hydrostatic pressure, that is pressure exerted by liquids. So we will demonstrate, or I will actually demonstrate to you all, that the pressure at the same level is the same value. So the pressure exerted by a liquid at the same level is the same in all directions. To do that, again we need to have colored water. Normal water is sufficient, but as I told you all before, when we have colored water, the visibility is better. And then I have this bottle, a plastic bottle. Here in this bottle, I have made all the holes at the same level in all different directions, but at the same level. That is the important thing. That is what we are going to observe now. Pressure exerted by liquids at the same level is the same. So then you all know the activity. We need to fill water into this. Once we fill it completely, then I can take it out of the water. Then you all need to observe how water exits through the holes. So now you will be able to see, you can see here, students, how the water exits. Can you all see? it's coming out through all the holes, and as well you can see it's coming out with the same speed. All the holes are at the same level. You can see it exiting with the same speed. And again, y'all can observe when the amount of water decreases, the speed decreases. That of course y'all can understand. So from that observation, I am sure y'all can understand that a liquid exerts the same amount of pressure at the same level in all different directions. Okay, students. So now another characteristic, already you all know when we say hydrostatic pressure, pressure is exerted in all directions and in all levels. Then we saw that pressure at the same level is the same. Now I am going to demonstrate that the pressure changes with the depth of the liquid column or the water column. Or for that matter, we can understand that the pressure increases with the depth of the liquid column. So to do that, again I have the colored water. You all know the reason. It's more clear to observe how the water exits through the holes. And then I have this bottle here, a plastic bottle with holes at the same line, along the same line, but at different levels. So I'll be filling water into this, and then you will have to observe how water exits through the different holes. We will have to fill water to the maximum. Now I will Can you all see, students, how water exits through the holes? Can you all see from the top, it comes out with less speed. But whereas from the bottom holes, it comes out with more faster. And also the distance to which the water is pushed out is longer from the bottom holes and shorter from the top holes. Can you all see here? This is more longer, this is shorter. So from this, now even here you can see this goes far, this is short. So from this observation, what can we conclude? Now we all can understand that the pressure at depth, or when the depth of the water increases, the pressure exerted by that water increases. So at the top the pressure was less. As we went down, as the holes go down, as the depth of the water increases, the pressure increases. That is why water is pushed out with higher pressure. So that's why it goes to a more longer distance. I am sure you all can understand that. Okay, students. So now we are going to observe how pressure is transmitted through a liquid. What is the machine that is used using this principle? It is the hydraulic press. But when we use that concept to lift a vehicle, we call it the hydraulic hoist. So first I'll demonstrate how pressure is transmitted through the liquid. So to do that, I have two syringes. So you all can see, students, this is a large syringe with a piston here, and this one you can see is a small syringe with a piston. Now in both you all have to observe clearly the liquid level. Again here I am using colored water so that the changes are more clearly visible. So here you can see the piston is in contact with the liquid, and in this cylinder also you can see the piston is in contact with the liquid, and throughout the tube, that is through which the pressure will be transmitted, there is liquid, that is water. So what do we know now? I will apply a force to the small piston. Then you will have to observe what happens. when I press the small piston, you will have to observe what happens to the larger piston. So now you can see when I am applying a force, can you all observe the large piston? Slowly as I press the small one, the larger piston is being lifted up. Can you all see that? So if I release the pressure again, now you can see again the force acts on the other side. The large piston comes down. So from this, you all can understand that pressure is being transmitted through the liquid. So how do I transmit pressure or how do I apply pressure? When I give a force here, there is the area, the cross-sectional area, a small area there. With that area, I apply a certain amount of pressure. The same pressure will be transmitted through the liquid to the larger piston. Now here, if you look at the area, you can see that's a larger area. So you all know pressure is force over unit area. When the pressure is the same, when you apply a small force here on a small surface area, the force that acts on the larger area will be greater. We will be discussing calculations related to this as well. So here again I'll demonstrate. When we push this piston, you can see the large piston rising up. So their pressure is being transmitted through the liquid. And also there is a liquid column here. Now compared to the pressure exerted by this liquid column, the pressure by the force I apply is greater. Therefore, we neglect the pressure exerted by this liquid column in the large piston as well as the small piston. So we only consider the pressure exerted by us by exerting a force. So that concept is the hydraulic press. So now again I'll bring it back to normal. So we can observe how the hydraulic hoist is functioning. So here I have a car just to demonstrate what happens. So students, for us to observe it more clearly, I attach the car. You all know how the hydraulic press functions. Now this is the hydraulic hoist. The same principle, and we will see how the vehicle is being lifted up. So here of course I have connected the large piston to the stand so that it's easy for us to observe. Now I have the small piston here. Now you all can see there is a liquid connecting it. So then what happens when I apply a force to the small piston? There is pressure generated, pressure is exerted to the liquid that is transmitted to the large piston, and therefore there will be a force acting on the large piston that will lift the vehicle up or hoist the vehicle up. So here you all can observe clearly students when I apply a force to the small piston. Now here you can see the car is being lifted up. So as we apply the force, the car goes up. When we want to release it, you can release the pressure, apply the force in the opposite direction. So here you can see the car comes down. Now that is the function of a hydraulic hoist, the normal hoist. But here students, you all have to remember, now this is a toy car, so a small amount of water was enough to hoist it up. But for a real car, the weight of the car is more. So to apply that amount of pressure by applying a force to the small piston, we transmit the pressure, but we need a higher force acting upward so that the car, the real car or any vehicle for that matter, will be hoisted up. So to do that, it is difficult to press the small piston, because then you will need to have a very tall liquid column inside the small piston and you have to keep on pressing it for a longer time. So to facilitate that, what they do is in the real hydraulic press, they use a compressor. Now the compressor pumps liquid into this small piston. Instead of pressing it down, they pump the liquid. So by pumping the liquid, they exert a pressure to the larger piston. So easily the vehicle can be hoisted up. So that is the function of the hydraulic press or hydraulic hoist that we see in the garages or workstations. Okay, students. So now we will try to understand how gases exert pressure. Like solids and liquids, gases exert pressure due to their weight. Always weight acts downward, so because of that, they exert a pressure at the bottom surface of the container. That is one method. Then you all know about compressibility of gases. Gases can be compressed easily. How do we do that? By applying a force, we try to reduce the volume of the gas. So then gases get compressed. The same way, now I have inflated this balloon. When we say inflate a balloon, we try to accommodate a large volume of gas within the small volume here. So that means we have compressed air in this or compressed the gas inside the balloon. Then here I have this glass U-tube connected to the stand, and inside that I have colored water. Again, you all know, students, the reason for using colored water, it is more clearly visible. Here we will be observing how the levels of the water inside the two arms of the U-tube will change. That is what you need to observe. So it's more easy to observe when we have colored water. Now, as you can see, in both the arms, we have water, colored water, and you can see the levels of water inside the arms. In both the arms, it's the same. So, also you know that pressure at the same level of liquids is the same. So, that means at this surface and at this surface, the pressures are equal. So, that is when the balloon is not connected. So, I'm going to fix the balloon here. Now, observe clearly, students, the levels of water in the two arms are still the same. So, then what do we do? I will be loosening this knot around the mouth of the balloon so that the compressed air can escape in. So, now observe what will happen. Right. So, now I have taken off the twine there. Now can you see the levels? This is lower, this is higher. There is a difference there. What is the reason? Initially, air was compressed inside the balloon. Now when I remove the twine, the air comes out and the compressed air exerts a pressure onto this water surface. Due to that pressure, the water was pushed down here and the pressure was transmitted and the level rises up in the other arm. So from that, we can understand that air exerts a pressure or gases exert a pressure. And that pressure will be equal to the height difference. Now here you can see, students, if we take it, this is a rough idea I am giving you all. Otherwise, you can measure also. So from this level to this level, there is a height difference of about this much. So the pressure exerted by that liquid height is the difference between the pressures in both the arms. Now even if I push and exert some more pressure, if I try to release some air by pressing the balloon, you can see the water level further changes. Now when I release it normally, you all can see a small difference. When more force is applied, you can see how the pressure changes. So from that change, you all can understand that the compressed gas or compressed air exerts a pressure. And that pushes the liquid column down here, which rises up onto the other side. The difference in height of the liquid columns, from using that height, we can calculate the pressure exerted by the air inside the balloon. That is the pressure exerted by the air inside the balloon. You all know the equation H rho G. So, the height is going to be the difference in these two levels. I am sure you all can understand that, students. Okay, students. So, now we will try to understand how we use the siphon method. You all know atmospheric pressure helps us in different ways. So, one of the ways is the siphon method. Now, we'll consider this as a tank full of water. Normally, you all know we have fish tanks at home. So if you want to remove water from the fish tank, that is from this tank, if I want to transfer the water into this trough. Let's consider both are tanks. So from tank A into tank B if we want to transfer water. Now look at this tank. Now there's water inside it. At the surface of the water, what is the pressure? It's the atmospheric air that is acting on the surface, or it's above the surface, it is the atmospheric air. So that air exerts the pressure, that is the atmospheric pressure. So at the surface there is atmospheric pressure. Then if you take this water, this liquid column, there is a column, so that also exerts a pressure. And you all know the pressure at the surface is less compared to the pressure at the bottom. So what we will be doing is we will be using a tube, a rubber tube to transfer water, and here we will consider the sum of both the pressures. So here what I will have to do first is I will need to fill this rubber tube. Now there is water filled in the tube. What I will have to do is I will have to bring one end to the second tank, and from this end it has to go to the bottom, right to the bottom of this tank. Then only, as I explained to you all before, there will be a difference in pressure. At this end, it's only the atmospheric pressure. When I release my thumb, it will be exposed to the atmosphere. So there is only atmospheric pressure acting on this end. Whereas when I dip this into the bottom of the tank, there is pressure from the atmosphere. In addition to that, there is pressure from the water inside this tank. So there is a pressure difference. That pressure difference pushes the water from this end to this end, so that we can transfer the water. So now this is right at the bottom, and if I take my hands off, you can see the water coming out. Can you all understand this method now? There is pressure exerted by this column plus the atmospheric pressure. But here it's only the atmospheric pressure. So there is an additional pressure in this tank that pushes the water through the rubber tube. So that is the method that is known as siphon method. So using this method, we can transfer the water from one tank into another tank. And here another thing that you need to observe. Here students, this tank is slightly above the other tank. So here another thing, to facilitate the pressure difference, we have this tank above the second tank. So there also it's easy to maintain the pressure difference. So that is the siphon method. So I am sure you all can understand this method. This is an application of atmospheric pressure. Okay students. So another application of atmospheric pressure is the use of rubber suckers. You know why we use that? To hang different weights, different objects at home. It can be in your vehicle, or it can be in the kitchen, or in the storage cupboard. We can use these rubber suckers. So I'm sure you would have seen a rubber sucker. We have this surface that will be used to attach the rubber sucker onto the surface. Say the wall or a tile or even a glass is the surface to which we are going to attach the rubber sucker. And on this side, you all know there is a hook, so we can hang a weight or an object using this hook. So how does this rubber sucker function? Now you can see on this surface there is atmospheric air. So around it there is atmospheric air. So the pressure exerted by the atmospheric air acts on this surface as well as this surface. But when we press it to a surface, I'll explain it now and then I will demonstrate it. Now let's say if this is a glass surface, when I press it onto this surface, the air that is here will escape out. So because of that, if we just keep it this way, it won't stick. If we really press it, the air from inside the surface escapes out, but the air from the outside exerts a pressure onto the rubber sucker. Because of that, the rubber sucker sticks to the surface. Then you can hang a weight. So this is the way the rubber sucker sticks to the surface, gets attached to the surface. Now I have another rubber sucker because this is easier for me to attach it to a surface and to hang this weight. It's easier for me to use this one. So I'm going to demonstrate how we really use it at home. So what I will do is I will attach the rubber sucker to this surface. So here, once it is attached to the surface, it will not come out. So as I told you, the air inside will escape out. The pressure given by the atmosphere around it will keep the rubber sucker attached to the surface. So then this is a weight. So you all can see, students, this is a wooden block. This has a certain weight. Now if I hang it, now this is of course a slightly modified one so that we can easily hang the weight on the rubber sucker. So here you can see the weight can be hung like that. So this is an application of atmospheric pressure. So I will remove the weight. Now if you want to remove the rubber sucker, if you want to remove it back, if you just pull it, it won't come. Why? As I told you all, the air, the atmosphere is exerting a pressure that doesn't allow us to pull it out. So if I just take it off from the side, you can see it easily comes off. And for the rubber sucker to function properly, we need to have a smooth surface here, and this side also, it should not be damaged. So if we can make the air from this surface to go out, when we stick it to the surface, we can use it easily. So with that explanation, students, I am sure you all can understand the function of rubber sucker as an application of atmospheric pressure. Okay, students. So now we are going to do this activity in order to understand that a liquid exerts an upward thrust on an object that is partially or completely immersed in it. So to do that, I have a jar containing water here. So here, students, I have the Newton balance or the Newton spring balance. You are familiar with this balance. We have the two scales. Both the scales are there. You can see the gram scale on this side. You can see the Newton scale on the other side. So we can use this spring balance to measure the weight of objects or the force of the exerted onto this spring balance. So here, as I told you all, I have a weight. If I hang it here, you all can see the weight of the object. Can you all see the reading? You can see it is about 230 grams or 2.3 newtons. That is the weight of this object in air. Now, if I push this down, can you all look at the reading? The weight increases. So that means the force acting downwards increases. So when I push, I give a force downwards, you can see the total force, the resultant force increases. Now I will push the object up. I will give a push from the bottom. Now what can you see? The reading decreases. That is because I exerted a force in the opposite direction. The weight is acting downwards, I exerted a force upwards. So then there is a decrease in weight. You all can understand that. If we exert a force downwards, the weight increases, the reading increases. When we exert a force upwards, the force decreases. So that means the reading here decreases. Now we will see what will happen if we immerse this object in water. Observe the reading closely. Now I am immersing it. What can you see? Completely immersed in water. What is the reading? When we immerse this in water, what is the reading you all see? It's about 190 grams or 1.9 newtons. Earlier in air, the weight was 2.3 newtons. Now it is 1.9 newtons. So what is the observation? There is a reduction in weight. So reduction in weight means what is happening there? There is a force being exerted upwards. From the first two observations, you all know When there is a reduction in weight, that means there is a force acting upwards. So now here, what is the substance that exerted the force? It is water. So when you immerse an object partially or completely in a liquid, here it is water, in any liquid, the liquid exerts a force upwards. It exerts an upward thrust. That is what we call as upthrust. So when you immerse an object in a liquid, the liquid exerts an upthrust on that object. So I'm sure you all can understand that concept now. Okay, students. So from the previous activity, you all understood that all the liquids exert an upward thrust, the upthrust on an object immersed partially or completely in a liquid. So here as the liquid we use water. So water exerts an upthrust on the object. So here in this activity, I am trying to understand or demonstrate the relationship between the weight of the object when it is immersed partially or completely in water, and when we are immersing the object, there is a certain amount of water that will be displaced. So we will be collecting that water in another beaker and we will get the weight of that water that was displaced. And thereafter we will try to find the relationship between the upthrust, the weight of the water displaced, as well as you all know when we immerse the object in water, there is a reduction in weight. That also you all observed in the previous activity. So the reduction in weight. So there are three components: the reduction in weight, the upthrust, and the weight of the water displaced. We will try to understand the relationship between all three components. So to do that activity, I have slightly modified the activity here. Without holding the object and immersing it, I am going to use a stand so that I can easily hang the object to the particular point. So here these are the 4 stages in which we need to get the reading. So initially the object, now this is going to be the object. This is a set of balance, students. You all can see that there are 4 weights. So half volume is going to be 2 weights, full volume is going to be all 4 weights. So then it's easy for me to immerse it into the water as well. So initially the weight or the object has to be near the water surface. We need to take the reading of the spring balance as well as the weight of the beaker with water. Then the object has to be half submerged. Third instance where the object is completely submerged, and finally we need to have the object completely submerged but more into water. In the third instance the object will be completely submerged but closer to the surface of water. In the fourth instance it will be into water. So those are the 4 stages we will get the readings. So to start the activity, first I need to fill this jar. You all know this is a displacement jar. So in this, when we fill water, it will come to a certain level. Thereafter, after this point, the excess water will flow out. So that is what I am going to do now. I am going to add water. The excess water will flow out. So we will need to allow it for some time until all the water flows out. At the same time, students, what I am going to do is I am going to use the stable balance to measure the weight of the beaker containing water. It's 0. So we will place it here, and now you all can see the reading. 30 grams, so that means it is 0.3 Newton. So initially when we bring the object closer to the surface of water, there will be no water displaced from the displacement jar. So the reading of the beaker will be 0.3 newtons. At the same time, I will get the weight of the object. So here we will hang it. You all can see clearly, students, it's 4 Newton. So the weight of the object is 4 Newton. Weight of the beaker is 30 grams. So it's 0.3 Newton. Right. So now I'm going to first hang the Newton balance here. And then I will hang the weight. So here I have actually set it to a level where it is going to be near the surface of water. So that is in the middle, it's near the surface of water. It's not immersed, it's near the surface. So now I am going to remove this beaker. I will set the second beaker. Now we need to set it up so that now I have the beaker. So the displaced water will be collected inside the beaker. You can get the weight of the beaker with water in this. And initially you all can see, I will adjust it so that it becomes more closer to the water surface. So now the object is closer to the surface or near the surface. So students, now this is the first stage. The object is near the surface of water. Can you all see the Newton balance reading? It's 4 Newtons. And also you all can see the beaker, there's no water displaced. The beaker alone, the weight is 30 grams. So it's 0.3 Newtons. That is what I have to fill in here. This is 4 Newton and that is 0.3 Newton. Okay, students. So now I have to half submerge it in water. Now here it is half submerged. So you can see here, students, the water has been displaced. At this time, we need to look at the reading of the Newton balance as well as the reading of the beaker containing water. So can you all see the reading here, students? It's 3.7 Newtons there. So then at the same time, you have to get the reading from here as well. It's 60 grams. So that means it is 0.6 Newton. So that is what I will have to note down here. 3.7 Newton for the spring balance with the object hanging from it. And this is 0.6 Newton. So then what do? We need to completely immerse the object in water, but it has to be near the surface, near the water surface. So that is what I am going to do next. Now can you all see? It's completely immersed. Again, you need to get the reading. So here also you need to get the reading of the Newton balance as well as the beaker containing water. Look at them carefully. So here you can see, students, the Newton balance reading. It is 3.4 Newtons. At the same time, if we get the weight of the beaker with water, it's 90 grams. So it's 0.9 Newtons. That is what I need to enter here. 3.4 Newtons and this is 0.9 Newton. So now what do? We need to immerse the object further down into water, but it should not touch the bottom surface of the container. So what I will do is, I will immerse it further. but it is not touching the surface. Here you can see the reading, students. Reading of the Newton balance, it's 3.4 newtons. The same reading as before. And also the beaker containing water, that is also 90 grams. So that means that is 0.9 newtons. Is there a change? No. There is no change when the object is completely immersed in water. So if I write the reading here, that is again 3.4 newton and 0.9 newton. So those are the readings that we have obtained. So initially I had the object where it was near the surface, it was not immersed in water, and before that I got the reading when just in air. So the weight of the object, it was 4 newtons. At the same time, the beaker was 30 grams, so the weight of the beaker is 0.3 newtons. The same values were obtained when the object was near the surface, not immersed, near the surface. So again, the weight of the object was 4 newton and the beaker with displaced water, it was just 0.3 newtons. Then when we half submerged the object, you saw the reading decrease here, it became 3.7 and the beaker with water became 0.6 newtons. When completely immersed and near the surface, the reading of the object became 3.4. At the same time, the beaker containing water became 0.9. When you further immerse it below, away from the surface of water, still the readings remain the same. 3.4, the weight of the object, that is the Newton balance reading, and 0.9, the beaker containing water. So from these, what can you all see, students? You can see initially the weight of object in air 4 newton. But as we immerse it, partially immersed or half submerged, the weight decreased. Completely submerged also, the weight decreased. What is the reason? We understood that there is the upthrust acting upwards. Due to this upthrust, there is a reduction in weight. So that is the weight what we see when we immerse an object in water or for that matter liquid. So when an object is immersed in a liquid, there is an apparent weight. That means there is a weight loss. So we need to calculate the weight loss. So we have the beaker with displaced water. There you can calculate the weight of water. Then we can find the relationship between the loss of weight, the weight of water displaced, as well as the upthrust. So that is what we are going to establish using these values. Okay, students. So from the previous activity and the Archimedes principle, you all know that when an object is partially or completely immersed in a liquid, there is an upthrust exerted by the liquid. Due to the upthrust, there is a weight loss that is observed, and the weight that is observed when the object is immersed in a liquid is called the apparent weight. So now what we are trying to do is, if we take different objects, if we put them into water, here the liquid is water, so when you put them into water, they float in different ways. There can be an object that sinks in water. Then there can be an object that floats partially submerged in water. Another object floats completely submerged in water. Now we are trying to understand the reason behind this. So to do that only, we need these materials. So as I did before, I'm going to use a stand to fix the Newton balance so that it's easy for us to get the reading. Here I have a tank with water, a glass tank with water. And for the objects, now you all can either take bottles filled with sand to different levels. Here I have filled water to different levels. So that one will sink in water, the other one it will float completely submerged in water. The other one, it will float partially submerged in water. And also it's colored water so that you can easily understand and identify the objects. So first, if I show you all, now although I'm going to hold on to the thread, I will not be exerting a force after I put it into water. So here you can see once I put it into water, I am just holding it loose. So you can see the object floats in water, partially submerged in it. The same way, if I take this bottle, here you can see this is the object that floats completely submerged in water. The second type of object. Then we have the third object, the bottle filled completely with water. You will see if I keep on letting it, it will go down. So it sinks in water. So we have all three objects. Now I need to dry the outer surface so that I can take the weight of the objects. I will take the first object that will float partially submerged in water. So here if we take the weight of the object, you all can see there. So you can see the reading, students, it's 1.5 Newton. Can you all see the reading? So 1.5 Newton. Now what I am going to do is I am going to immerse it in water. So for that I will hang it in this stand. Now can you all see the reading? It has come to 0. Now it is partially submerged and floating in water, and at that time you can see the reading of the Newton balance 0. So that is what I need to enter here. So here initially the weight of the object was 1.5 Newton. Then the apparent weight, that is 0, and it is partially submerged. Partially submerged in water. So when we write as partially submerged, it's understood it's floating in water. So that is the first object. Initial weight, that is the weight of object in air, was 1.5 Newton. Apparent weight, you can see the reading, it's 0 Newton, and also the object is partially submerged and floating. So the second object, again you can see the weight. So here you all can see the reading of the Newton balance, 1.8 Newtons. The weight is 1.8 Newtons. Now again we will have to connect it here, and I will let it to float completely submerged in water. So here you can see we needed to bring the stand also down so that the thread is loose, so that there is no force exerted by the Newton balance, because it is completely submerged and floating in water. You all can see the reading, students. It is 0. Now the thread is straight, twine is straight, and the object is floating completely submerged in water. You can see the reading. The Newton balance reading is 0. So here the weight of the object was 1.8 Newton and the apparent weight is 0. So here it is completely submerged. Completely submerged in water. Then we have the next one. The third object, it's here. You can see the weight of the object as 2.5 Newton. Weight of the object is 2.5 Newton. So then if we immerse it into water, you will see, students, it will go down. there is a reading. Can you all see now? It is 0.5 newtons. Can you all see the reading? 0.5 newton. Okay, students. So we got the readings. Weight of the object was 2.5 newton, and you saw that there was a reading of 0.5 newton when the object sunk in water. And here we have to say it sinks in water or it's sunk. So now can you all understand the relationship? Whenever the object is completely or partially submerged in water, there was no apparent weight. But when the object sinks in water, there is a certain apparent weight. So from that, you all can understand when the object is partially or completely submerged in water, upthrust is equal to the weight of the object. But when it sinks in water or a liquid, the weight is greater than the upthrust exerted by the liquid. That is the conclusion that we can get from this activity. But with that, when we further do the calculations, you all can get a better understanding about the relationship between the upthrust and the weight of the object at different instances. Okay, students. So now we are going to observe how the hydrometer functions. You all are familiar with hydrometers. We learned this in the previous grade also, and I explained the function as well. So here you all can see the hydrometer, universal hydrometer, that is written here. And then you can see it's a glass tube with calibration. And at the bottom, you all can see the lead pebbles or lead shellings, that is to give a weight to this hydrometer, and it has been sealed and contained within this area. And you all know why this part has to be thin, so that you can put it into any thin container containing a liquid. So why do we use this hydrometer? We use a hydrometer to measure the density of liquids. So that is what is calibrated here. Now look at the calibration at the top, it's 0.7. But as you go down, you can see at this point it's 2. So that means the density is increasing as we go down in the calibration in the scale. So how does this function? What is the relationship between the hydrometer and the principle of flotation? When you put an object into a liquid, the liquid exerts an upthrust. Due to the upthrust, you all can remember the objects are pushed upwards. Then they can be submerged at different levels and float in water. So that principle is used to measure the densities. Now when a liquid is less dense, the upthrust it exerts is less. And when the density of the liquid is high, the upthrust is more. So then what will happen is, in a less denser liquid, the hydrometer will go down. Whereas in a more denser liquid, the hydrometer will be pushed upwards. We will look at the reading in water. Here I have water. You all can see the density. What is the value? 1 gram per centimeter cube or 1000 kilograms per decimeter cube. That is the value you can see there. 1 gram per centimeter cube. So that the density of water 1 gram per centimeter cube. That you all know. So in water it is floating at this particular level. If the liquid was more denser, the hydrometer will be pushed up. Then you will get a higher reading. If the liquid is less denser, hydrometer will sink in. We have discussed that before also. So then you will get a lesser reading. So this hydrometer functions based on the principle of flotation.